How's it going, Professor?
Hello,
Brought to you
Professor.
live. Brought to you live on a Sunday. Brought to you live here by Moy's house on a sunny day in
What are
San
you
Diego.
saying?
Today, we're gonna take the first brilliant project, make an improvement so grand that your mind will be blown away. Here's what we're gonna do. We're gonna
GTA.
simulate in a video game. What's the video game?
GTA. I don't know if you know, Professor. One of the most popular ones, but yeah.
And what
Get a
we're gonna
code.
do with GTA is apply a couple of different concepts. Riemann sums. Then we're gonna do integration the way we learned how to do it, and we're gonna check it. We're gonna check our calculus with the game, because the game has metrics. So with the game, we're able to record speed and then also distance traveled. So we'll check if we're right, and using a few different ways to find it with the calculus we learned in the second part of the semester. Okay, let's do 0 to 100. We're gonna speed up as fast as we can. We're gonna make sure it's a straight road. Speed up as fast as we can, accelerate as fast as we can. And then once we reach the max speed, we'll go for about 20 seconds. And what we're gonna do is we're gonna take timestamps. We're gonna timestamps in each second. And each second will be a timestamp, and then they'll create our curve. And that's gonna be a speed curve, velocity curve. And the integral of the velocity will be the distance. So the end goal will be to find the distance traveled using the speed metric, and then we'll do that with calculus, and we'll check that with the game's metrics, which tells us how much distance we covered, to see if math works. Also, last thought, the curve function, we could do it using some math websites. Desmos maybe could do it, other websites that could auto do it, but
Or
yeah, the function's gonna be a bit of an estimate.
We're ready to do the GTA. As you can tell, my car right there, really fast.
Right below the screen, as you can see,
Got the
there is
car
a
going.
car going, and then there's a stopwatch, and
And
the
here's
two
the-
variables we'll be measuring, we'll be taking in, we'll do it in 1 second. So every second we'll take a point. We'll take the speed, which we can see on camera, and then relative to the time. And then we're gonna use integration to measure the distance. What we're gonna do is we're gonna use regression parameters using Desmos. So we're gonna take the 20 points, and it's gonna make a function for us with A and B, A being the max speed it approaches. It's not gonna be perfect, and B being basically how fast it took to get there. And it's a common physics equation that we're gonna use, which is Vt equals A, and then in brackets 1 minus E to the negative Bt, closed off parentheses. So I'm not claiming I got that from the top of my head. This is a common physics and engineering equation that is commonly used to model how your speed changes over time. So I know my speed is going to start at 0. It's increasing quickly at first, and
Only gets
and
to
then,
100.
right, or whatever max speed it gets to, that's what we're going to test. And then it's going to increase more slowly, flattening out. So this models real life, car acceleration, and it never passes that certain limit, that max speed. So, not claiming that I know this is a commonly used for acceleration and speed, and we're going to use this. We're going to plot the points in Desmos. We're going to get our A and our B, which will get our function. Then we'll integrate, get the distance from the speed as a function of time, and then compare it to the metrics that we record in GTS to see if math works. Also, to demonstrate other understanding, we'll do some Riemann sums with that. So on the left we have distance, so that's going to show us how much distance we travel. Then we have speed on the top and the time. Yeah, that's good.
Ready?
Maybe encountering some police here. Okay, so now we are looking at the video. We're gonna plot 20 seconds of data points.
Yep.
From these, we'll get the regression model, get the function, and do the integration.
1 second is 20 seconds, right, Philip? It's 20, right?
Yeah. It was 1 second and already 30.
Yeah.
And when I say estimate, still, if it's around 20 seconds, Okay, next we're gonna get our A's and B's. So Moises, you're gonna go to the next line. Scroll, yep, yep, perfect. Scroll down. Now we're gonna get our regression parameters. We're gonna get A and B. So we're gonna start with y1 approximately 2a in parentheses 1 minus e. Oh, 1 minus e. To the negative b times x. So 1 minus e to the negative b times x1 times x1 parentheses. Like that. Oh, too many. Perfect. Oh. There we go. Alright, Professor. So now we got a line from 0 to 20. I'm going to zoom in. From 0 to 20 is, you know, the points we're going to be measuring. Right there. This is regression parameters, and now we're going to get a little bit more of a precise equation. So more one line below, you're going to type our equation, since we now have our A and B's. Alright. So the equation is velocity as a function of time equals A. All the numbers, all the decimals. Even though it's not precise, we make it as precise as possible. And then in parentheses we got 1 minus e to the parentheses to the negative b times 5, you know, all that. 0.15 9282 times t parentheses. There we go. Perfect. So now we've got a curve that we can work with, because speed is obviously inconsistent. Like it's not gonna be a perfect curve, but we got a curve that is a line of best fit using our plot points. What we're gonna do now is we're gonna tell Desmos to give us the answer of integration, so then when we do it actually using calculus and doing it ourselves, we compare it and it looks good. Okay, so we're going to be doing the integration equation, and it gives us 1476, and we're going to divide that by 3600 because we're doing it in seconds. So when we do that, let's do a new one. Because the x we measured was second interval, whereas the speed we're measuring is miles per hour. So yeah, it's 3,600 seconds in 1 hour. Let's see what it gives us. And this should be the distance traveled. Okay, the distance in GTA was 0.37 miles. This is 0.41. Reason being we're a bit off is, look, this is not a perfect fit. It's a linear regression fit. Not linear, but it's a regression model, which allows us to use calculus, because we can't just do it off of points. It's never that perfect in real life. And the game is a bit off. Yeah, and the video game is not 100% accurate. So yeah, game's calculations a bit off. It is pretty close, which proves that the math works. Math works. So now this is the answer, and now we're gonna actually do it ourselves with integration and using the function, as well as we'll use Riemann sums. Okay, so now that we've got the answer that works with the regression, approximately, we're gonna do it using math to demonstrate our understanding of integrals. So here's the original equation. It's gonna be bounds is 0 to 20 because it was 20 seconds. Okay, let's do this. So we're gonna pull the constant out. The constant is a, which is the max speed. Again, it's not perfect, but that's the max speed. Pull it out, and we're gonna separate this and this. So 0, you'll see me doing work here. Perfect. Okay. Stop it. So for the exponential part, for the e part, we know that e for constant times t. When we're trying to integrate that, we're going to pull the constant out like this, and then times kt plus c. So in this case, when k is 0.159282, this is going to become negative 1 over 0.159282 times e to that same constant t. And now we apply the 20 and we apply the 0. So let's do that. Stop it. So now when we're doing this, it's gonna be negative 1,59282 times e to this constant times 20, which with a calculator it comes out to 3.1564, and then that is minus e to the 0, which we all know is 1. So now we calculate that. Let's quickly do the calculator. This becomes, and we got to remember that's negative. So what that becomes is 0.04184 and minus 1. So we pull this down, negative 1 over 0.159282 times negative 0.95816. Let's finish the calculation. Let's divide it. Is going to come out to 6.01567. So that's for the e side. Now this side, well, when we integrate just 1, that obviously becomes x, or in this case t. So then we do, that's just 20 and then minus 0. So 20 minus 0 is 0. Then we do 20 minus 6.01567, which is 13.98433. And then finally, multiplied to the constant, 105.6197, which was our a, times that altogether comes out to around 1476.47. Okay, we got to remember this is in terms of seconds, whereas the speed was in terms of miles per hour. So what we're going to do is we're going to divide this all by 3,600 because it's 3,600 seconds in 1 hour. And finally, we get around 0.41. Math works. Okay, so we've done the calculations. V of 5 it will come out to around 54.58. We have 10. We've done all the calculations, come out to 182.65. We have 15 around 96.17. We have 20 around 105.60. So now what we're going to do is we're going to add all these together and then multiply by delta t. So $338.90 and then times by 5, which will come out to, I'm going to do the calculator. Okay, 169.6.31. So as we can see, when we compared to the perfect, let's say, value of the integral, which is 1,476, this number. So really quickly, one may ask, like, why did we multiply by 5? Why did we multiply by the width of the rectangle? Well, how do you find area on a 2D scale? It's going to be width times length. So our v of t, which is our y, is going to be our length, and width will be 5. So it's all right.
Times 4, I mean.
Now, underneath, lastly, to finish off the project, this amazing, wonderful project brought to you by McDonald's. We're going to show what happens when we do the midpoint Raymond sums with n equals 10. So let's say this is 20, this is 0. We want to find the area under the curve. And n equals 10. So first we're gonna do the calculation for the width of the rectangle, and we'll do delta t equals 20 over minus 0, which is again obviously 20, over 10, which is the number of rectangles we want to have, equals to 2. So that's going to be the width of a rectangle. So if we have 10 rectangles, we need to think about this a little bit, and the width is going to be 2. We want to evaluate the midpoints, so that's obviously going to be at 1, 3, 5, all the odd numbers up till 20. So first number 10, 5, 8, 4, 4. It's obviously not your best drawing, but it should do. For purposes, we'll do the 100, 50, 25, 75. Okay, it's something like that. Again, not perfect. And now let's do the calculations. So this was Raymond sum n equals 4, and here we'll do midpoint Raymond sum n equals 10. We're gonna evaluate here v of t at the odd numbers, 1, 3, 5, on and on. Okay, so let's do them all. We'll see you when we're done with the calculations. And then,
why'd you do that then?
alright, we've done all the calculations. So for here, we're going to plug in 1 for t. Then we're going to do for 3, 5, 7, 9, 11, 13, 15, 17, 19. Which goes to 10 rectangles. This was around 15.50. And 3 around 37.74. 554.48, 67.90. Just writing down all the answers we got from the calculator. Oop, 50. Wait, no, I messed this up. 93.45. Apologies. Okay, now I'm gonna add all these values up. Let me do, and we get to 739.57. So that's our length, and then we're gonna multiply by the width times 2, which comes to much closer number. This is a really good estimate, and let's compare this with the calculus. So 147.9.15, and this is 1,476.4. So we're 3 numbers off. It's a great estimate. Riemann sums, you know, the more rectangles you use, the better it's going to get. And if you're at midpoint, it's usually good, assuming the curve is a nice smooth curve. So here's Riemann sums. We're going to show a clear picture at the end, as well as the picture of the calculus we did to find the integral. And remember, this number is per second, is distance per second, and we are doing obviously a rate of speed at miles per hour. So if we want to, you know, do it properly, we'll divide this by 3,600, and this as well by 3,600, and we get the speed we want. But yeah, this shows how much closer it is to the answer. And yep, that's our project, Professor. I hope you have a great summer.
Thanks, Professor. Thanks for everything.